This is a 6-bit adder-subtractor calculator. It can take two 6-bit numbers and add them together or subtract them. It features 6 hexadecimal displays, 2 to display each input number and 2 to display the resulting number of our operations. It also features a 7-segment display, which will give us a negative sign whenever the result happens to be negative. Our circuit also features a key, which consists of a single bit that allows us to switch operations on the calculator. The key connects to two LED lights that can display us which operation is currently active. When the key value is 0, we get addition. When it is 1, we get subtraction. We can also see an overflow indicator in our circuit. When this LED light is on, that means our operation produced overflow. Now let's test some numbers to see how operations work. It is important to remember these displays are hexadecimal displays. Thus, they will not display the numbers in typical decimal fashion. I can write here the number 8. And the display will be seemingly a decimal display. Here is the 9. The difference starts appearing once you try to display a 10. In the decimal system, 10 would be represented by a 1 and a 0. But since this is a hexadecimal display, it represents 10 as a 0 and an A, 11 as B, 12 as C, all the way up to 15, which is represented by 0F. Now let's perform an operation. Let's do 2 plus 8. First, let's make sure our operation is set correctly in the LEDs. I want addition. Now let's put in the binary numbers for 2 and 8 as A plus B respectively. Our result is 0A, which, as I mentioned earlier, is hexadecimal for 10. Alternatively, we can subtract 8 from 2 by simply switching the key's value. A continues to be 2 and B continues to be 8. The result we received was the number -0.6, which is hexadecimal for -6. Feel free to test the calculator using the link in the description. A and B should be able to take any absolute value in 6-bit binary, not mattering which is greater. The possible operations are always A plus B or A minus B. Now let's look into the main components of our circuit. It has 3 of them: a 6-bit adder-subtractor, a selective splitter, and a 2's complement to binary conversion tool. Let's go over the adder-subtractor first. This is the most important component of the calculator, since it performs all our mathematical operations. The smallest part of our circuitry is our full 1-bit adder. Here's what it looks like. I will not go over the construction of this adder, since it is a very standard and well-known circuit. It simply takes two 1-bit numbers and adds them together, producing a result and a carryout. It can also take a carry from a previous addition and adds it into the operation. Once these 1-bit adders are joined in a circuit for 6-bit numbers, it looks like this. They connect corresponding bits from the numbers in the operation and produce the bits used to construct the answer. These bits are joined up by a splitter, which will turn 6 1-bit numbers into a single 6-bit number. The adder-subtractor also produces 1 extra bit, which connects to the overflow LED indicator. Now, the same circuit is also capable of doing subtraction, utilizing 2's complement. It does that through these XOR gates, laid out before each B entry, in the adders. All these XOR gates are connected to a key bit. Yes, this is the same bit used in our key which allows to switch operations. Let us remind ourselves. On the 0 position, the calculator performs addition. On the 1 position, it performs subtraction. This value goes here, into our adder subtractor subcircuit. If the value of our key is 1, the XOR gates will flip the results coming from the number b. The 1 will also go into the carry in used in the first adder. This produces the 2's complement of b and then adds it to a. Using this method, it doesn't matter whether a is greater than b or vice versa. If b is in fact greater than a and we perform a subtraction, our result will be in 2's complement as well, and will require a conversion to binary in order to be displayed in our hexadecimal displays. I'll go over that process later when I show you the 2's complement to binary conversion tool. For now, we need only to observe the subcircuit performs both addition and subtraction, and we produce a 6-bit number as a result, as well as an overflow indicator. Now let's look into the next component of our circuit, the selective splitter. This is probably the simplest component. All it does is take the 6-bit number we produced in our adder subtractor and copies the leftmost bit into a separate output. The number is unaltered. The copied bit will be used later along with the key used to switch operations to turn on the negative sign display if our numbers happen to be negative. The next component is the 2's complement to binary conversion tool. This is not very different from our adder subtractor. Also uses 6 1-bit adders. The aim of this tool is to detect whether or not the result is in 2's complement. It does this by checking these 2 conditions on the AND gate. The keys correspond to the sign obtained from the splitter and the key used to select the operation. If both have the value of 1, the tool will be activated, and we convert the 2's complement number into binary and give it a separate sign bit. It does this by taking the resulting 1 from the AND gate and using it repeatedly into the adder inputs. This is the equivalent of subtracting 1 in 2's complement from the number we inputted. Then these results will go into the XOR gates, also connected to this AND gate. They will flip the bits of the results. In other words, we are taking a 2's complement number, subtracting 1, and flipping the bits. This is the reversed operation used to convert a binary number to 2's complement. Thus, it successfully transforms the 2's complement number to binary. Here is a test. I'm writing here the 2's complement of 7. Once I set both my keys to 1, we get 7 in binary as a result. This result will go into the displays. This extra bit produced will go into the 7-segment display to show a negative sign. So this is it. This is the 6-bit calculator. Hope you have enjoyed.